Hello ma'am, we have done our reading into 4 parts, that are MAC protocol for static WSN, MAC protocol for mobile WSN, multi-channel MAC protocols, and MAC protocol for underwater WSN. And under static MAC protocols, we have read up to 13 protocols, that are SMAC, TMAC, PMAC, PADAMAC, PAMAS, PMAC, ZMAC, Shift, Trama, CCMAC, MHMAC, and Crankshaft. So I am going to present SMAC. So the primary goal of SMAC is to reduce energy consumption, but it also achieves good scalability and collision avoidance by utilizing a combined scheduling and contention schemes. There are major sources of energy wastage in CSMA like ideal listening, collision, large control overhead, over emitting. So SMAC tries to reduce all this. It has three major components: periodic listen and sleep, overhearing and collision avoidance, and message passing. So SMAC communication cycle is divided into 2 parts. Active period and sleep period. Active period at which the node is going to awake, and sleep period when the node is going to sleep. Awake period is again divided into 2 parts, one in which synchronization takes place, and on the other data communication takes place. So the basic idea behind SNAC, that is sensor MAC protocol, is based on periodic sleep listen schedules and synchronization. So the neighboring nodes form clusters to set up a common sleep schedule, and if two neighboring nodes reside in two different clusters, then they can wake up at listen periods of both the clusters. So schedule exchanges are accomplished by sync packets broadcast to immediate neighbors, and the period for each node to send a sync packet is called a synchronization period, and collision avoidance is achieved by carrier sense. Furthermore, RTS CTS exchanges are used for unicast type data packets. A very important concept of SMAC is it divides long messages into a frames and then sent it into a burst, but it also has some disadvantages, like it add delays in the system, and that's why it should be built for the applications that are latency intolerant. So TMAC, that is timeout MAC, it doesn't solve the additional issues in SMAC, but rather it optimizes delay in more sleep-wake pattern. So TMAC is a contention-based medium access control protocol. It is same as SMAC, but it has adaptive duty cycle. So it adaptively setting the length of active portion of the frames, and it tries to reduce that time interval where communication doesn't take place. So instead of keeping the transceiver on, it switches off the transceiver. Communication that is done in TMAC is same as SMAC. That is, communication is divided into synchronization and data communication, but by adaptively ending the active period, TMAC protocol nodes may save energy by reducing the amount of time they spend idle listening, and it adapts to changes in traffic conditions. So the timeout period is set to span a small contention period and an RTS data exchange. So if a node does not detect any activity within that timeout interval, it can safely assume that no neighbor wants to communicate with it and goes to sleep. On the other hand, like if the node engages or overhears a communication, it simply starts a new timeout after that communication finishes. So to save energy, a node turns off its radio while waiting for other communication to finish. But it also has a disadvantage, like there might be a RTS packet after timeout, so it introduces additional delay in the system. So to improve this, future RTS is proposed, so sensor nodes can use future RTS to inform the next hop that it has a future message transfer. So the future RTS is attempt to solve the problem of early sleeping, and TMAC also considers the buffer size of the sensor nodes when calculating the contention period. So sensor nodes that have full buffer may take a higher priority and control the channel. So this way limits the buffer overflow and buffer overflow of sensor nodes. Advantages of TMAC. TMAC has the same performance as SMAC under constant traffic, but saves more energy under variable traffic because it has adaptive duty cycle and it has a minimum throughput.
My first protocol is BMAC, or Berkeley Media Access Control. BMAC is a carrier sense media access protocol for WSNs which aims to provide a low power operations, effective collision avoidance and high channel utilization. BMAC supports on-the-fly configuration. Unlike SMAC protocols that provides network organization functionality along with the link layer protocol, BMAC gives these functionalities like that of organizing the network or synchronization, etc. on top of its implementation. It provides a set of interfaces that allow services to tune it according to their requirements. These services can be turned off and on as per the requirement. Thus, we can say that BMAC is a pure link layer protocol that uses channel assessment and packet backoff for channel arbitration, link layer acknowledgement for reliability, and low power listening for low power communication. To determine if the channel is clear or not, it uses clear channel assessment technique. It uses a software automatic gain control to estimate the noise floor. Signal strength samples are taken. The median of the queue in which these signal samples are stored is added to an exponentially weighted moving average with a decay alpha. The median is used as a simple low-pass filter to add robustness to the noise floor estimate. This robustness is used because the noise level changes depending on the environment. Signal strength samples are taken after transmitting a packet or when the data path of the radio is not receiving any valid data. To avoid false negatives in the reading, the BMAC searches for outliers in the received signals such that the channel energy is significantly lower than the noise floor. If an outlier exists, it declares that the channel is free because a valid packet does not have such a low outlier. If for n samples we have no outliers, then the channel is declared as busy. As mentioned earlier, BMAC allows to turn off or turn on the CCA feature. By disabling CCA, a scheduling protocol may be implemented above BMAC. BMAC also gives link layer acknowledgement support. If acknowledgements are enabled, BMAC immediately transfers an acknowledgement code after receiving a unicast packet. If the transmitting node receives the acknowledgement, an acknowledgement bit is set in sender's transmission message buffer. Each time the node wakes up, it turns on the radio and checks for the activity. If activity is detected, the node powers up and stays awake for the time required to receive the incoming packet. After reception, the node returns to sleep. If no packet is received, a timeout forces the node back to sleep. To reliably receive the data, the preamble length is matched to the interval that the channel is checked for the activity. If the channel is checked for every 100 milliseconds, the preamble must be at least 100 milliseconds long for a node to wake up, detect activity on the channel and receive the preamble, and then the receive message is received. The advantages of BMAC are that it may be configured to run at extremely low duty cycles and does not force applications to incur the overhead of synchronization and state maintenance. With one transmitter, BMAC outperforms SMAC in the broadcast mode by 2.5 times and SMAC unicast mode by at least 4.5 times. BMAC performs well in the broadcast mode due to the more sophisticated CCA and lower preamble overhead. For the unicast traffic, BMAC is better because SMAC suffers from the overhead of RTS and CTS exchange.
Power-aware multi-access protocol with signaling for ad hoc networks, also known as PAMAs, is a protocol for ad hoc networks which is a combination of MACA and the idea of using a separate signaling channel. Now in this protocol, there are separate signaling channels for RTS and CTS. So the main point of focus in this protocol is to save power, and the behavior does not change the delay or throughput in the network. In this protocol, the node may be in 6 states: idle, await CTS, binary, exponential backoff, await packet, receive packet, and transmit packet. So when a node begins receiving a packet, it enters the receive packet state and immediately transmits a busy tone. If the node hears an RTS transmission or noise over the control channel at any time during the period that it is receiving a packet, it transmits a busy tone. This ensures that the neighbor transmitting the RTS will not receive the expected CTS. It also solves the hidden terminal problem. Now, these are the power conservation behavior of PAMAs. As we can see that under light load conditions for large number of nodes, the amount of energy savings is 20%, and in uniform traffic, in heavy load conditions, it is 15% without control overhead and 12.5% with control overhead. Under light load conditions, as n tends to infinity, the power savings due to PAMAs is bounded by 75%, and under heavy load conditions, the power savings range from 30 to 40%, in n ranging from 10 to 20. So, as we saw that power savings by PAMAs range from 10% to 70% without affecting delay or throughput. Another advantage of this protocol is that we can easily incorporate this protocol with other protocols such as PAMA and MOCOM. Thank you. ZMAC is a network protocol for wireless sensor networks. It is a contention-based protocol which is a combination of CSMA and TDMA. Under low contention, it focuses on high channel utilization, and under high contention, it acts like TDMA and focuses on reducing collision among two hop networks. Now, the protocol begins with a setup phase including 4 steps: construction of the network topology, also known as neighbor discovery, distribution of time slots, local framing, and network-wide synchronization. Now, this initialization causes a high load on the network, which is made up from the perspective of the developer with long service life and efficient data transfer. After activation, each sensor node transmits every second ping for 30 seconds. Pings are sent back immediately from sender to receiver, usually to check connection and line quality. With ZMAC, the ping contains information on the sending node itself and all the information that has been collected through the direct neighbors of the node. By pinging the environment experienced by a sensor node, the nodes it directly contacts and what it can contact indirectly with an intermediate station are known. Now, coming to the advantages, this is useful under applications which where high data rates are expected and 2-hop contention is medium to high. As shown in this graph, ZMAC performs better than BMAC under medium to high contention. ZMAC uses knowledge of topology to improve MAC performance under high contention. Thank you.
CCMAC, or correlation-based collaborative MAC protocol. Current media access protocols focuses primarily on reducing energy consumption by introducing sleep-wake patterns. However, these protocols generally transfer redundant data with increased latency. Suppose an event is detected by 10 nodes in the network, then it is not necessary that all 10 of them should send their information to the sink. Even if one node out of those 10 nodes send the information, it will be sufficient. The CCMAC protocols try to exploit this nature of the WSNs. CCMAC protocols aims to select a representing node for a region of the radius known as correlation radius. The sink of the network runs an iterative node selection algorithm which determines this radius. This information is broadcasted to every sensor node during network setup phase. When a node is accessing the medium to send its data to the sink, then correlation must be used so as to avoid sending redundant information. Once the packet is in the network, it must be reliably sent to the sink, because now it is only the one information of its kind, because all the redundant information has been filtered out. So this route through packet becomes more important than the intermediate generated data packets by the routing nodes. CCMAC has two functionalities corresponding to this source and router functionalities of the nodes. Emac filters out the correlated data and Nmac prioritizes the route through packet. In the RTS, CTS and data packets, a new field name first hop is used. When a sensor records an event, it sets the FH bit in RTS data packet. Emac. All nodes sets the FH field in the RTS, CTS data packets and try to gain access of the medium. When any node captures the medium for transmission, it becomes a representing node of that particular area. The neighbor nodes listen for RTS CTS packets to determine the type of functionality. Along with this, the nodes calculate their distance from the representing node. If a node finds that its distance is less than the correlation radius, then it is known that it is inside the correlating region of the node that is representing that region. So this particular node stops its transmission. Otherwise, if the distance is greater than correlation radius, then it will contest for the medium if it wants to send the packet. These are the two cases for the Emac. On the left hand side, we can see that the transmission radius of the representing node is greater than the correlation radius. In this case, the neighboring node stops its own communication and performs functionality of routing other node packets. In order to conserve energy, every such node enters a sleep state for some duration. On the right hand side, we can see that the transmission radius is less than the correlation radius. In this case, some nodes are outside the transmission range but are inside the correlation radius. This means that some nodes will not get information about their correlated data. This will result in the contention of the medium from their side. We can inform these nodes by using some extra transmissions, but this adds to the overhead of the protocol. Another problem is to route the packets of the representing node out of the correlation region. Since the nodes in the communication range are all part of correlation region, if they follow the sleep-wake pattern, then the packet will never move out of the region. To solve this, a directional sleeping technique is used. In this technique, after the first contention phase, all the neighbor nodes drop the packets that are in their queue. They do not try to send the packet for some duration, but listens to the channel so as to route any packets from the representing node. If after some number of transmissions, node does not receive an RTS packet for itself, it will conclude that it is not in the path of data transmission from the representing node to the sink, so it will go to the sleep state. Nmac. When a packet is routed to the sink, it may come across a node that has its own data to send, but since the route through packet has high priority, so it is forwarded. When a correlation neighbor receives an RTS regarding a route through packet during the random listening period, it switches from the sleep state to receive state and receives the packet. During the transmission, the representative node defers its transmission and route through packet is received by the correlation neighbor. Advantages of CCMAC. In the high traffic load, CCMAC outperforms all the contention-based protocols. This is due to the fact that it does not allow the correlated neighbor to send packets while representing node is sending the data. So basically it filters out the redundant information from the network. Goodput of CCMA is about 180% higher than SMAC and other contention-based protocols. The CCMAC protocol consumes 25% less energy compared to TMAC and 70% less energy compared to SMAC and TRAMA protocols.
Now we will discuss another protocol for networks with static nodes. TRAMA, which stands for Traffic Adaptive Media Access Protocol, consists of three parts. The first is called Neighbor Protocol, in which the nodes distribute the location of their one-hop neighbors among each other. At the end of this protocol, all nodes have the topology information of their two-hop neighbors. Now the second part begins, which is called Schedule Exchange Protocol. It establishes and maintains traffic-based schedule information after the nodes exchange their schedules. At last, It uses an adaptive election algorithm which selects the node for data transfer and allow other nodes to sleep. This makes the system very energy efficient. This election algorithm attempts to reuse transmission slot in case if the node selected for transmission does not have any data to transfer, hence improving the throughput of the network. Some of the features of this protocol are: it is energy efficient because of a great sleep-wake pattern that it follows. It is a high energy efficient system. It has very high throughput as it reuses the bandwidth for data transmission in case there is a slot available. It has high delay like any other schedule-based algorithm, which have higher delay compared to contention-based MAC protocols. So it has high delay like any other schedule-based protocol. It is inefficient for mobile nodes even though it has a random access period which allows it to add mobile nodes, but the energy efficiency of the system decreases a lot when this is done.
In the series of mobile MAC protocol, the next protocol we are going to see is Multi-Mode Hybrid MAC protocol, in short MHMAC protocol. MHMAC protocol is designed to support cross-layering application for packetizing radios. It is a hybrid protocol that is contention based as well as contention free. It can work in synchronous, asynchronous and full-on mode. This protocol has an ability to change its mode depending upon the traffic condition and requirements. It also allows the node belonging to different nodes in common cluster. So the first mode we are going to see is full-on mode. It is applicable for very low delay requirement and busy traffic. In full-on mode, nodes will be always in awake state. Hence, this mode consumes lot of energy and not usually preferred. In this, data packets are preceded by RTS and CTS and are acknowledged. Asynchronous mode is selected in case of low power sporadic communication with seldom traffic. For data transmission in this mode, a sequence of preambles, twice the time of duty cycle period, is transmitted by sender to ensure that receiver is awake at the time of sending of data packet. The preambles mainly contains two fields. One is the destination address, second one is the missing preamble time to the data transmission. Unicast receiver sends the acknowledgement signal as soon as it awakes and hence shortening the preamble duration, but in case of broadcast, complete preamble sequence is required. The latter field is used for overhearing protection as broadcast receiver will schedule its sleep till the beginning of packet transmission and unicast sender will schedule its sleep period while waiting to send packet and receive preambles destined to someone else. It also uses shut-up packet to handle preamble collisions. It includes active sender address and its missing preamble time, which allows other sender to sleep until end of the data transmission. After data packet transmission, it is acknowledged in case of unicast transmission and receiver node stays awake for some time, waiting for next period before going to sleep state. Synchronous node is selected in case of data burst or periodic traffic. In this mode, nodes run synchronizes duty cycle and each duty cycle period is divided into fixed length sequence of slots, which is public or dedicated. Synchronization is done by sending sparse sync packet contains the local address, local slot assignment and a hop counter. Sync packet has a validity of 180 seconds and its information is discarded after that interval. Public slots reserve 15 milliseconds for max signaling and premium packets and the remaining 85 seconds for all kind of traffics. Nodes run contention-based protocol in public slot in which sender scans the network and runs a backup timer before sending the data packet. Unicast packets are preceded by RTS and CTS and also acknowledged. If no energy is sensed in network for 25 seconds, then receiver nodes go into sleep. Dedicated slots are reserved for unicast communication between two slots, where sender node run backoff timer before sending the packet and packet get acknowledged by the receiver node. When node changes its state, it is required to notify the neighboring nodes about the transition. For that, it uses hello packet, which contain a state field and slot reserve bit (SR bit), which when set implies to request to ask for dedicated slots. To notify neighbors, hello packets are broadcasted in asynchronous mode. For a node to change its state from asynchronous to synchronous, it broadcasts hello packet preceded by a sequence of preambles. Receiving nodes after processing and random backoff transmits a request packet which also contains SR bit, which when set implies asking for dedicated slot. Using request OK exchange, dedicated slot is decided by the synchronization node for each request packet received. Once the synchronization process ends, MHMAX sends synchronized turn event and the list of neighbor with its assigned dedicated slot to sender's application. It also broadcasts sync packet to notify others node that they can start their synchronization. In order to prevent the collision of packets while synchronization, only one node is allowed to do synchronization at a time. The duration of the state transition from the asynchronous state to synchronous state on each node is equal to the preamble duration, that is, twice the duty cycle period plus a varying time between 1100 millisecond and 1100 millisecond plus the duty cycle time. Dedicated slots can be exchanged later also by running request OK packet exchange. Since the number of slot is limited, so it is possible that every node not get its dedicated slot, so they communicate via public slots.
Crankshaft protocol used for static wireless sensor networks. The basic principle of the protocol is that nodes are only awake to receive messages at fixed offsets from the start of the frame. Communication in Crankshaft protocol divide time into frames, and each frame is divided into slots. So there are two types of slots in the Crankshaft: broadcast slot and the unicast slot. During broadcast slot, all nodes wake up to listen for an incoming message, and any node that has a broadcast message to send contends with all other nodes to send that message. A frame starts with all the unicast slots followed by a broadcast slot, and each node also listens for one unicast slot every frame. So during that slot, a neighboring node can send a message to that node only if it wins the contention. A node's MAC address is also used here to determine the slot to which the node listens to. Hence, the node that wants to send a message knows precisely that in which slot the destination wakes up. Crankshaft protocol also provide special provisions for sync and destination nodes, because sync and destination nodes has more traffic as compared to normal nodes, therefore they require larger bandwidth. Hence, sync nodes use special MAC addresses to determine whether the node is sync node or not. So each frame has n unicast slot, and the slot assignment is performed by calculating the MAC addresses. So the period between the start of the slot and the moment the listening nodes listen to its radio is used to resolve the contention. So in the contention window, node chooses a particular slot to which it wants to send a message. So the sending node listens for a short amount of time before chosen moment to find if any other node contending for the same slot. So if not any other nodes are sending that, then sending node starts sending preamble to notify that other nodes about its intention to send. So shortly after receiving node is known to wake up, the sending nodes transmit the start symbol and the actual message. So during the contention window, only the contending receivers are awake, and the winner of the contention is awake more than a short pole, hence results in efficient energy contention resolution. So advantages and disadvantages. So it reduces overhearing and communication grouping by letting nodes power down their radios alternatively rather than simultaneously, and disadvantage is that cannot provide good broadcast flood delivery, very rigid structure, hence limits the applicability of the protocol.
In this series of slides, we are going to see how the MAC protocol works in case of mobile network. First and the foremost question is, why we require separate MAC protocol for mobile nodes network? Can we use protocol design for static scenario in mobile case also? The answer is yes, we can, but the network performance will be very poor. The reason for the bad performance are: first, as all static MAC protocol uses some kind of sleep-wake pattern for energy efficient performance. If sensor nodes are mobile, then it may possible that node misses the wake interval of its neighboring nodes and results in the drop of the data packet. Second, nodes require to be synced with its neighbor in order to know its sleep-wake pattern, which happen by sending sync packets in active period. For mobile nodes, neighbors are continuously changing, so it requires frequent sync packet transmission with variable frequency, which is not supported by static MAC protocol. Now these are the list of few MAC protocols which support the mobile network which we are going to cover. The first protocol for mobile network we are going to see is MS-MAC protocol. Here MS is stand for mobile sensor. MS-MAC is the first protocol designed for mobile WSN. It is a modification of SMAC protocol, which is a contention based protocol. In case of static network, it works similar to SMAC protocol. Therefore, it has all the characteristics of SMAC. For mobile network, it has an extra feature of active zone formation around the mobile nodes, which deals the mobility in the network. But unlike SMAC protocol, the rate of the resynchronization is variable in this case. Frequency at which the resynchronization takes place depends upon the speed of the mobile node. Using signal strength of the sync packet, one can determine the speed of the mobile node, and this information shared among the other nodes using extra field added in the sync packet which contain the speed of the node. Now, its working is classified into two parts, static case and mobile case. Since in static case, its working, which includes synchronization, schedule selection, virtual cluster formation, and data transmission, is similar to SMAC protocol, and we already discussed this, so here we are going to discuss about mobile case only. In mobile case, mobile node sends sync packet to its neighbor. Because of the difference in the energy of the sync packet, neighboring nodes can detect its mobility and form an active zone. If the nodes present in the 2 hop distance from the mobile nodes are in the same cluster, then no active zone formation takes place. But once mobile nodes move close to the boundary of a virtual cluster, then active zone formed around the mobile nodes. Synchronization frequency of all the nodes present inside the active zone increases depending upon the speed of the mobile node. As the synchronization frequency increases, so now the schedule table of mobile node get updated more frequently and it need not to wait for longer period of time. So when it enters into the new cluster, it get updated about the new schedule more frequently and hence the data packet miss probability decreases. Now these are the few advantages and disadvantages of MS-MAC protocol. So the first advantage of MS-MAC protocol is its mobility and speed aware MAC protocol. And the second is it works energy efficiently in both stationary as well as in mobile condition, but up to a medium speed. Now for disadvantage, first is to detect high speed mobility, some nodes require to be awake for a whole period of time. As a result, some node may die early and this degraded the network performance. And the second is it works for the limited number of mobile nodes. Next protocol we are going to see is Mobility Adaptive Protocol. MMAC protocol tries to overcome the limitation of MS-MAC protocol. It is unsynchronized protocol which combines the advantage of both synchronous protocol and random wake-up protocols in order to improve the throughput of the network. That means node will wake up randomly. Unlike the MS-MAC, it will use beacon and acknowledge for data transmission instead of RTS and CTS. Now frame of MMAC protocol consists of carrier sense, beacon and wait period. The main function of a beacon is to inform the neighboring nodes that sending node starts listening, and after the beacon, the sender node wait for the acknowledge from the neighboring nodes in wait period. Nodes wake up randomly as they are not synchronized with each other. Once the node wakes up, it requires to tell its neighbor that it is listening. For that, after carrier sense, a beacon is broadcasted by it which contains the identifier of the sending node. Since the neighbors are not synchronized, it may possible that neighboring node unable to receive the beacon and nodes are unable to communicate with each other. Now it may possible that two or more nodes try to communicate with same destination node at the same instant of time, which may cause collision. To prevent this collision, each contending node acquires the backup delay according to the priority assigned by the coordinator, which is not a random value. And this is a stage 1 of a protocol. After every successful data transfer, node will acquire new delay value from the coordinator according to the priority status to give fair chance to other competing node in stage 4. To ensure nodes can communicate with each other, it is necessary that sender node listen for receiver node before sending the data. Once the node is ready with the data which is to be transmitted, it starts listening for the beacon of the destination node. After receiving the beacon, sender node will acknowledge the beacon with acknowledge and followed by the data transmission. The first advantage of a MMAC protocol is it won't require synchronization. And the second is occupancy of channel is minimal. For disadvantage, latency in transmitting the data once the data is ready with sender node is more. Next mobile MAC protocol we are going to look at is mobile MHMAC protocol. As name suggested, it is a mobile extension of MHMAC protocol which introduces new mechanism to improve MHMAC mobility support. Similar to MHMAC protocol, it is a hybrid protocol with multi-mode operation. It is specially designed to tolerate asynchronous mobile nodes in the neighborhood of synchronous nodes and provide fast transition and interference mitigation mechanism. It is used in scenario where speed of the mobile node is very high. Its characteristics are similar to MHMAC protocol, with little modification in mechanism to improve mobility support. Modifications are: first, synchronous nodes can terminate the preamble transmission from asynchronous neighbor and network activity may sampled in synchronous idle slots. This will reduce the interference between synchronous and asynchronous nodes. Sync packets now can be transmitted in any slot, which increases the sync frequency. This will improve the capacity of protocol to track faster nodes. Mechanism to associate to neighbor nodes, reserve slots and transmit data is simplified, which allows this protocol to associate with neighborhood nodes in very less time. Similar to MHMAC protocol, it also operates in multiple modes, that is synchronous, asynchronous and full-on mode. Its working is similar to MHMAC protocol. Now the first mode is asynchronous mode. Asynchronous mode is not affected by mobility. Active and passive interference mitigation methods are combined by MMHMAC protocol in order to improve the throughput of synchronous node in the presence of asynchronous transmission node. Active interference mitigation is done using setup packet. This protocol allows synchronous node to interrupt sequence of preamble using setup frame. For this, an extra field is added in setup frame to inform whether the interruption is due to collision or synchronous neighbor node. In case of collision, interruption node goes into sleep state, whereas in case of synchronous node interruption, node stays awake and waits for the sync packet. This is one more bit added in the preambles, which define whether sender allows receiver to interrupt its preamble sequence. Passive interference mitigation is based on the alignment of asynchronous node active state and public slot of synchronous node. This will reduce the preamble overhead so that new asynchronous node can quickly synchronize with any synchronous node. Now the next mode is synchronous mode. For dealing with mobility in this mode, it is required to increase the sync frame frequency. For that, an extra field is introduced into sync frame that defines the sync sending instant relative to the beginning of the duty cycle period. The sync frame identifies the sender's address, the sync period, the dedicated slot allocation vector with the assigned dedicated slot, the slot when it was sent, and the offset in relation to the beginning of the slots in multiple of 10 milliseconds. The interval reserved for MAC signaling is also increased to 50 milliseconds. MMHMAC uses sync frames to detect the changes with respect to neighbor nodes. Nodes update its table when it receives new sync frame with an RSSI value above the threshold value, and delete the entry if no sync is received after 2.5 times the sync period. This protocol reduces synchronization overhead as it allows the request OK frame exchange to occur at any time and to be effective immediately. It may cause improbable allocation overlap and hence result in collision, which is later detected and corrected when the dedicated slot's allocation vector on the sync frames are compared. Each sync packet entry lasts for 4 duty cycles by default after the last sync reception. During the data transmission by synchronous node, if destination node state is unknown, then it will transmit the data in the second part of the public node with preamble preceded the data packet. Now in mode change, it allows the asynchronous to synchronize with synchronous node with a single request OK packet after receiving the sync packet. Advantage of MMH MAC protocol is first, it allows nodes in different access mode to coexist in the same region. Second, it can track faster nodes. Third, the association time of mobile node is very less. And the last is synchronous node throughput is high while communicating with asynchronous node.
Now we will discuss another protocol for sensor networks with mobile nodes. MMAC, which stands for Mobility Adaptive Collision Free Medium Access Control Protocol. As MMAC works like trauma in case of static nodes, we will only focus on the part of MMAC that deals with mobile nodes. It faces two major issues, which are mobility information, which is solved by introducing cluster heads, and synchronization, which is solved by introducing global synchronization period. The problem with mobility information is that individual nodes can predict their future mobility state. But for the algorithm to work, each node also requires future state of current and potential two hop neighbors. So cluster heads are formed which share this information, and the synchronization problem occurs as individual node can independently calculate frame times, which leads to a synchronization problem. To take care of this problem, after calculating individual frame times, the nodes do not adjust the number of schedule access slots on their own, but send this frame time to the head of cluster, which takes the average of these time frames and after sharing this with another cluster head, introduces a global synchronization period in which all the nodes synchronize. The main features of this protocol are it manages a large number of mobile nodes very well, and it is less energy efficient for static nodes. So for a system consisting of static nodes, we do not use this protocol, but it is highly efficient for a system with mobile nodes. Another protocol for mobile nodes is Hybrid MAC protocol or CTH MAC protocol, which is a combination of CSMA-CA and TDMA protocol. It works on the assumption that all the data is to be transferred to one master node in the middle of the network. This is called the sync node. The sensor nodes are randomly distributed around the sync node in a 3D space. It also assumes that the master node is aware of the initial position and initial velocity of all the sensor nodes. Now the sensor nodes are divided into subsets and the master node allocates time slot to all subsets using a TDMA scheme. After this, all nodes in one subset contend for transmission opportunity as in CSMA-CA scheme. The master node sends a wake signal every time it wants data transfer to begin, hence giving chance to new mobile nodes to connect to the network. The outermost subset is the first to transfer data towards the sink, and the other nodes behave as a relay for the outer layer. After the outermost subset has sent all its data, the next subset starts data transfer, and this continues till the innermost set of nodes have finished their data. The main feature of this protocol are that it is energy efficient in case of high-speed mobile nodes, and it has a good throughput because it have only one node that collects all the data.
Category is multi-channel MAC protocol. These protocols are basically used in the applications like body area network and structural health monitoring, which requires high amount of data to be collected at faster rate. And multi-channel protocols are designed with an objective of maximizing throughput of WSNs by coordinating the transmissions over multi-frequency channels. These protocols have advantage of interference and contention-free parallel transmission on different channels. In multi-channel MAC protocol, each node has assigned a particular channel to transmit the data. There are several methods to reduce the impact of interference, such as transmission power control, creating medium interface sync trees, and, and many more. There are many in multi-channels MAC protocols available, but we are discussing some of them like MMSN, HiMAC, TMPC, MCLMAC, and YMAC. So, first we begin with MMSN. MMSN protocol is the first multi-frequency MAC protocol especially designed for WSN, which is composed of hundreds of simple devices geographically dispersed in an ad hoc network over a large geographic area. Each device is equipped with a single transceiver and the packet size is very small, approximately 30 to 50 bytes. It is a slotted CSMA protocol and at the beginning of each time slot node need to contend for the medium before they can transmit. MMSN assign channel to the receiver. When a node intend to transmit a packet, it has to listen for the incoming packet both on its own frequency and the destination frequency. MMSN protocol consists of two aspects, frequency assignment and the media access. In the frequency assignment, each node is assigned the physical frequency for data reception. The assigned frequency broadcasts to its neighbor so that each node know what frequency is used to transmit unicast packet to each of its neighbor. In WSN, frequency assignment can be done once at the beginning of the system deployment or it can be done very infrequently just for adaptation to system aging. After the frequency assignment, with the assigned frequencies, nodes cooperate to maximize parallel transmission among neighboring space in media access to provide efficient broadcast support. Nodes are time synchronized during media access and a time slot consists of broadcast contention period and the transmission period. During the broadcast period, nodes compete for the same broadcast frequency and during the transmission period, nodes compete for shared unicast frequencies. The transition period also provides enough time actually to transmit or receive a broadcast or unicast packet. The time slot size depends on the number of nodes that compete for the same frequency and the data packet size. The regular time slot is 3 to 5 milliseconds. Within, within one time slot, a node can either transmit or receive one packet. Each node first checks the broadcast frequency for receiving and transmitting a broadcast packet. If there is no broadcast packet to transmit or receive, unicast packet transmission and reception are considered. Each node behavior differs depending on whether it has one packet to transmit or not, as well as whether it has a unicast packet or a broadcast packet to transmit. If we are talking about its performance, then in MMSN, when more physical frequencies are used, more nodes are able to conduct simultaneous transmission without any collision. So the aggregate MAC throughput increases and the fewer nodes are assigned to use the same frequency within two hops. So communication interface decreases, which leads to less backoff and decreased channel access delay, and it also decreases the communication interface, which leads to less packet loss and more useful data packets are successfully delivered with the same amount of energy. And its advantages like MMSN always achieve a higher performance when more frequency are available. When the number of frequency increases and the gossip traffic is used, the packet delivery ratio increases. The aggregate MAC throughput increases and the average channel access delay decreases, so the MMSN become more energy efficient. Similar performance can be seen if its exhibit many-to-many traffic pattern is used. And its main drawback is at the start of each time slot, all nodes are required to listen on a common channel in order to exchange control information, which simply increase the protocol overhead. Now we are talking about our next multi-channel MAC protocol, that is HiMAC protocol. HiMAC is a hybrid TDMA-FDMA MAC protocol suitable for WSN applications in which data gathered by sensor nodes has to be delivered to at least one base station in a timely manner. HiMAC is the first sensor net MAC protocol that schedules the network nodes in a way that eliminates collisions. The functionality of HiMAC is independent of its underlying synchronization protocol. The communication period is composed of many frames, and each frame is equally divided into several fixed time slots, where a slot duration is the time required to transmit a maximum sized packet. A fixed number of consecutive slots in each cycle are scheduled slots, while the remaining slots of that cycle are its contention slots. An appropriate frequency as well as the specific time slots will be allotted to each node by the base station. Scheduled nodes will be able to communicate in an energy efficient, collision free manner by turning off its radio when it is not necessary. And all scheduled nodes employ low power listening on contention slots, during which they randomly select one slot to send a hello message to the base station. All the unscheduled nodes, which are just joined the network, only operate in contention slots, similarly sending the hello message. If a node hears a hello message from any other node in its one hop distance, it adds the sender to its neighbor list. The updated neighbor list will be included in the next hello message sent by that node. And based on that received hello message sent by the node, the base station can construct the schedule and send it to each node in a scheduled message. Consequently, every node will be able to send data message to its parent using its assigned slot and frequency in a way that maximizes the network throughput and minimize the overall uplink delay. In figure, it is shown the HiMAC packet format, in which you can see the hello packet, schedule packet and data packet format. Next, if we are talking about its performance, then there is a trade-off of performance and number of required time slots. In HiMAC, a fewer number of available frequencies result in a larger number of time slots, because if the maximum number of available frequencies is already reached, the node is assigned a new time slot instead to avoid the potential interference. Therefore, high performance leads to an increase in the number of time slot needed. And if you're talking about its advantages, then it is designed to provide high throughput and small bounded end-to-end delay for the packet exchange between each node and the base station. And its main drawback is that it enhances the protocol control overhead and it complicates the implementation.
MCP MAC protocol. It is a tree-based multi-channel protocol which is specifically designed for data collection applications in WSN. It uses a coarse-grained channel assignment strategy instead of node-level assignment, and also try to avoid complex coordination scheme by reducing channel switching and communication among nodes with different channels. When the sensor network have a dominant traffic pattern where multiple informations flow generated at sensor nodes converge to the base station, and if the data collection scheme built under some tree structure connecting the base station and trees, and then forward the packets along the tree. However, with a single channel transmission collision within the tree and flow congestion
at nodes significantly decrease the network performance. To solve this issue, TMCP used for data collection application in WSNs, and it is a realistic and efficient multi-channel medium access protocol for WSN. The idea of using multi-channel is to partition the whole network into multiple vertex disjoint subtrees, all rooted at the base station, and allocate different channels to each subtree, and then forward each flow only along its corresponding subtree as shown in figure. This scheme can work well with a small number of channels and has a straightforward transmission scheme without the need for synchronization at nodes, which makes it suitable for practical WSNs. TMCP is divided into three components: channel detection, channel assignment, data communication. In channel detection module, find available orthogonal channel that can be used in the current environment. Channel assignment module partitions the whole network into subtrees and assign one unique channel to each subtree. This is a crucial part of TMCP. The goal of partitioning is to decrease potential interface as much as possible. After partitioning, interface in the original network can be divided into two categories: interface among different trees, that is called inter-tree interference, which is eliminated by assigning different orthogonal channels to each subtree. And second one is potential interface, which is among nodes within a tree, that is intra-tree interface. Because the same channel is assigned to all nodes of one subtree, the intra-tree interface cannot be avoided and becomes a main reason which affects the performance of this protocol. So the goal of partitioning is to avoid network into subtrees, each of which has lower intra-tree interface. After assigning channels, the DC component manages the data collection through each subtree. When a node wants to send information to the base station, it just uploads packet along the subtree whom which it belongs. It is assumed that the base station is equipped with multiple radio transceivers, each of which works on one different channel because of the tree-based channel assignment strategy. DC is very simple without the need for time synchronization. Also, the base station can use this network structure to perform data dissemination. When the base station wants to send command or update the code, it can send out packet through all transceivers, and then packet will go through every subtree and reach all nodes in network. If we are talking about its performance, then by splitting traffic into different subtrees, TMCP decreases radio collision as well as traffic congestion, which leads to higher packet delivery ratio and lower latency. TMCP can significantly improve network throughput while maintaining high packet delivery ratio and low delivery latency, and outperforms other multi-channel protocols. By splitting traffic into different subtrees, TMCP decreases radio collision as well as traffic congestion, which leads to higher packet delivery ratio and lower latency. There are some advantages of it also, which are: it shows good scalability, and it also exhibits better performance in heavy workload. TMCP also more tolerant with respect to system load variations. And its main disadvantage is TMCP is designed to support converged cast traffic, and it is difficult to have successful broadcast due to partition. Furthermore, contention inside the branches is not resolved since the nodes communicate on the same channel, and the communication between nodes in different subtrees is blocked. So adjacent channels are not used, and therefore the limit bandwidth is not fully utilized. WiMAX protocol. It is an energy efficient multi-channel protocol, and it is used for dense wireless network applications. It is based on scheduled access. However, time is divided into several fixed length frames, and each frame is composed of a broadcast period, and a unicast period. Every node must wake up at the start of the broadcast period to exchange broadcast messages. And if there are no incoming broadcast messages, then each node turn off its radio. In WiMAX protocol, we can increase the number of possible time slots using multi-channels. Here, we can see the structure of WiMAX protocol. In this, there is a slots for broadcast period and for unicast period. Since several channels are available, a sender and receiver have to select the same communication channel as well as the transmission timing. In WiMAX, sensor nodes synchronize with their upcoming timer events by exchanging the timer remaining in the current superframe period. This scheme can be easily implemented by adjusting the expiration times of timer events. WiMAX protocol separates broadcast traffic from unicast traffic and makes broadcasting is more reliable than in the other MAC protocol. If not detects a network partition, then it goes into sleep mode to save energy. To reassociate with the network, the radio is periodically turned on to perform the bootstrap phase. Unless node receives any control messages, the radio is turned off again. Initially, the sleep interval is short, but whenever a node wakes but fails to rejoin the network, the interval doubles to save energy consumption from periodic listening. This protocol using a distributed method based time slot assignment algorithm. Every node maintains a slot allocation vector for storing occupied time slots within its one-hop neighborhood, including itself. Each bit in the slot allocation vector is set if the time slot at the same position is occupied. This information about the time slot assignment is broadcast with the control messages. After completing its initial time synchronization, each node collects information about occupied time slot in its two-hop neighborhood by ORing slots allocation vector upon receiving a control messages. The collection time must be greater than the control message interval so that it allows for the possible loss of control messages. Control messages, here we can see it consists node access, occupying time slot, slot allocation vector, sequence number, and the information for time synchronization. If a node runs out of a battery or removed from the network, the time slot that has been used by that node must be released for future use. A node is considered to have been removed when its control messages has not arrived during a predefined time, and neighboring nodes update their slot allocation vector once the removal of the node is done. The medium access design of WiMAX is based on synchronous low power listening, and only the contention winner can transmit a message to the destination node. Contention between potential sender is resolved in the contention window. The node wishing to send a packet sets a random backoff value within the contention window. When the backoff timer is fixed, the node wakes up and checks the medium for a certain amount of time. And if the channel is clear, a preamble is transmitted until the end of the contention window to suppress competing transmissions, so that receiver wakes up at the end of the contention window to receive data part of the messages, and if it receives no signal from the neighboring node, the receiver node turns off its radio device. If we are talking about its performance, then in WiMAX protocol, the average duty cycle remains low because the overhearing problem is reduced by allocating receive time slots to the nodes, and the delivery latency is slightly higher than the theoretical average delivery latency, which is half of the frame length. And the average data reception rate of WiMAX remains relatively high because a receiver can receive a series of messages by using multiple channels. It avoids a redundant channel assignment by not allocating a fixed channel to the node. If we're talking about its advantage, WiMAX has some advantages like it achieves a reasonable reception rate under high traffic condition, and as we say, delivery latency remains steady since a contention loser can retry in the next time slot in the next channel. And it also achieves low duty cycle under light traffic conditions. And its main drawback is it increased contention, especially around the sink node with high data rate scenario, which is hard to solve. Our last multi-channel MAC protocol is MC-LMAC protocol. It is a schedule-based single radio multi-channel MAC protocol which is designed with the objective of maximizing the throughput of WSN by coordinating transmission over multiple frequency channels. It is based on the single channel LMAC protocol and node select a time slot and a channel on which it is allowed to transmit. As we can show here, figure on the left is the state diagram for the node while executing the MC-LMAC protocol, and figure at the right shows the state diagram which for the node while following the schedule in MC-LMAC. So in the initialization state, node sample the medium for an incoming packet to enter the synchronization state. Synchronization is achieved by a hierarchical scheme started by the sync node and continues hop by hop as each node synchronizes with its parent node. If the time difference is detected, the node roll back to the initialization state. A time slot and a channel pair are occupied if the received signal of the transmission during the time slot on the channel is above a threshold, or if a neighbor node is already receiving from another node during the time slot on a channel. In time slot and channel selection state, node keeps a bit vector for storing the information about the slots occupied by neighbor. A node performs an OR operation over each bit vector per channel and discovers the free slots on different channels. And at the last stage, node stays in medium access state that follow the schedule according to the state diagram which node follow while following the schedule in MC-LMAC. Here, a time slot consisting of common frequency phase and a split phase. In the common frequency phase, all nodes switch to the common control channel to address their destinations and to be informed whether they are addressed in the current slot. In the split phase, senders and intended receivers or the nodes they are in discovery state, which switch to the channel on which data in the control message transmission will take place. Here we can see the slot structure of MC-LMAC. The number of CF slots is equal to the number of channels, and it is determined at the initialization of the network, and it does not change. And there are some advantages like there is no frequent channel switching in MC-LMAC, and it helps to maximize the throughput of the channel. And it has some disadvantages also like in MC-LMAC, overhead of the control message used for synchronization and channel and time slot selection. It gets worse as network density increase. There are total 5 multi-channels which we are discussing, multi-channel MAC protocol. Here we discuss total 5 multi-channel MAC protocol. For further discussion, we will discuss about underwater MAC protocols.
This part of video describes about various type of underwater protocols. We can't use the terrestrial protocol for underwater applications because of various disadvantages associated with them. First, terrestrial protocols make use of RF signals for communication, which suffers huge attenuation underwater, therefore makes them unsuitable for such applications. Second, the underwater nodes are inaccessible, therefore the underlying protocol has to be very efficient in terms of energy. So because of all such disadvantages, we are not using the terrestrial protocols for our underwater applications. So the first protocol in this section is the ERMAC protocol, which stands for Efficiency Reservation MAC. So now let's discuss about this protocol. ERMAC stands for Efficiency Reservation MAC. So in case of ERMAC, we are having a centralized deployment in which the sync node is present at the center and it is collecting information from all the surrounding sensor nodes. This sync node is responsible for data aggregation and communication towards the base station. Thus, we require heterogeneous nodes in this case. Now, let's look at the mechanism of ERMAC. So, in ERMAC, the whole communication cycle is being broken up into multiple time slots, which are further divided into mini time slots. Also, we are having two types of group. First, the distance group, and second, the direction group. In distance group, it is consisting of all the nodes which are having a particular distance from the sync node, and in case of direction node, it is having all such nodes which are communicating in the same time slots. So now let's look how these groups are going to be formed. So the sync node broadcasts a beacon signal containing information regarding the distance group, time slots, mini slots, and the sending timestamp. Upon receiving this beacon, each node gets to know about their distance group based upon the propagation delay of this packet. Then the sensor node replies back with the reservation packet in order to reserve their time slot. Then this RP is also heard by the D2 node and they figure out the node of D1 which is closest to them so that they can also book the time slot. So in this manner, each node is allotted a time slot and during data transfer, phase data will be transmitted from inside to the outside. So now let's look at the advantages. So in this protocol, we are having zero probability of collisions because of the transmission delay present. And also this protocol is having an inbuilt time synchronization mechanism. So it will remove the overhead of time synchronization. RMAC is the extended version of RMAC protocol. So now let's look at the network characteristics in terms of RMAC protocol. This protocol is based upon the concept of data mule. So in this case, we are having AUV, which is acting as a data mule. This AUV stands for Autonomous Underwater Vehicle, which is used to collect information from all the cluster nodes which are present under the water. So this AUV will be sent periodically in order to collect information from all the cluster nodes. And also the nodes will be of homogeneous type. That is, all nodes are of same type. Let's look at the intercluster communication. For intercluster communication, we are basically using the original RMAC protocol in which each cluster node is having a dedicated time slot, and during that time slot only it can communicate, and for rest of the time slot it is in sleep condition. And these time slots are assigned by the cluster head during the cluster formation. Now in order to accommodate the communication between the cluster heads and the data mule, we are extending the basic time frame of the RMAC protocol. So this extension part is used for communicating with the data mule. So whenever a data mule or the AUV arrives, it sends beacon signals for 2 time frame. So this notifies the cluster head that a beacon has arrived and it should get ready for communication. So for that, the client sends back ready packet to the AUV in order to notify its arrival. And once the ready packet is received by the AUV, it sends the data towards the cluster head. Once the data is received by the cluster head sends back acknowledgement towards the AUV. So in this manner, the AUV and the cluster heads are communicating with each other. Now let's look at the advantages. So in this case, the AUV is collecting data from all the cluster heads and the cluster heads are collecting the data from all the cluster nodes. So there is no need for individual node to communicate directly towards the base station. So by doing such arrangement, we are saving lot of energy. And also this protocol is very flexible and scalable because the clusters will be formed every time whenever new node will appear.
LPTSA. This protocol selects the slot allocation scheme on the basis of instantaneous network load. This adapts to the dynamic networks and also increases the throughput. The crucial part of the protocol is how to fuse TDMA and CSMA-CA to determine the switching threshold as a function of number of competitors in the network. The slot allocation is selected according to the load of the current network, and then the optimal access mode is chosen according to the relative priority of the slave nodes and the optimal number of backup stages. A low energy efficient distributed time synchronization algorithm is used. The moving node first broadcasts a plurality of time beacon packets to save nodes to be synchronized. The slave nodes to be synchronized use the reception time difference between consecutive beacon packets and the absolute time difference in the beacon packet for linear fitting, thereby realizing synchronization of nodes in the network. If a slave node has to send the data, the RTS is sent for the channel reservation. If there is a collision with another slave node, the slave node performs a random backoff for a period of time and then attempts to compete again. The host node counts the number of competitors according to the number of RTS received and then determines the size of the network load. According to that network load, the time slot allocation scheme is determined. When the number of competitors is greater than, say, a number n and the time slots are continuously distributed, CSMA-CA is used first. When a collision happens, the total number of experienced backoff stages is increased by 1. If the number of experienced backoff stages of a slave node is equal to the maximum allowed number of backoff stages and the number of slave nodes is greater than 1, the host node broadcasts access mode switches to TDMA. When the number of competitors is less than n and the time slots are uniformly distributed, the slave nodes with a high priority use TDMA to transmit data packets and the slave nodes with low priority use CSMA-CA. The location allocation of the time slots can be performed in various ways, such as continuous allocation, uniform allocation, and random allocation. Uniform allocation of time slots can ensure low delay and delay jitters. The continuous allocation mode can achieve higher throughput for a CSMA-CA. Therefore, when the load is large, the continuous allocation is selected to obtain higher throughput, and when the node is small, the slave nodes with high priority use TDMA. Due to large delay caused by TDMA, uniform allocation is used to ensure lower delay and delay jitter. When the load is small, the time slots are uniformly allocated, and when the load is large, the time slots are continuously allocated. As we can see, in the network with a small number of competitors, LPTSA performs better than TDMA, CSMA-CA, HCR, and HMAC protocols. It has a medium throughput, but it has a very less end-to-end delay as compared to CSMA-CA. The overhead for this protocol is less as compared to CSMA-CA, and a medium complexity and energy consumption is also low. Similarly, for a network with a large number of competitors, this protocol performs better than TDMA, CSMA-CA, and HCR and HMAC protocol. It provides us with a high throughput, a very low end-to-end delay, a less overhead, and energy consumption is also less. UNMAC. This protocol is a distributed, scalable, energy-efficient media access control protocol that is suited for underwater acoustic medium. This protocol performs well despite long and unknown propagation delays underwater. This is meant for delay-tolerant applications. Primary reason for not using MAC protocols used in terrestrial sensor networks is that the underwater systems experiences a very large propagation delays. All these MAC protocols take an assumption that the propagation delay among the nodes is very small. There was the use of FDMA-based protocols for underwater systems, but they were found to be very restrictive and poor in bandwidth utilization. Using CSMA-CA-based protocols causes overhead in terms of energy consumption due to exchange of RTS and CDS packets. In this protocol, a node, say A, broadcasts a sync packet at the beginning of its communication cycle period. It then goes to sleep by turning off its transceiver to save energy. The neighbor node of A, say node B, hears this packet and gets to know the length of the transmission cycle period. However, here we assume that the propagation delay is constant from one clock cycle to the next, and also the clock drift is not significant in one cycle. This protocol implements a topology control layer that keeps track of the neighbors of a node for whom this node is to remain awake for its transmission. The initial transmission time is selected independently and randomly by each node. Once a transmit time is fixed, the node always transmits message at that time only. To avoid collisions, we have a cycle period much longer than the transmit duration. Each node compares the neighbor list with the list of the nodes from which it has successfully received signals. After this comparison, the node generates the missing node list. This list is sent as a header of the data packet in its next cycle. Also, every node also sends a cycle period stamp in their sync header, which may be different from the one that was decided during initialization period. Due to this, a node has the option to change its current cycle period. Whenever a new node joins the network, if it hears from another node, it sends a hello packet to that node to inform it about its transmission schedule. A node may not receive a data at the defined time slots because of the channel issues, or maybe the sender node has failed. When a node does not hear from any of its neighbor, it puts that node in the missing node list. Then it announces through its missing header that it has not heard from one of its neighbor node. In one of the cases, that neighbor node may not have been able to communicate due to the channel issue. In such case, it will send a hello packet to the node as if it was a new node in the network. Hence, the receiver node will now get this new schedule of its neighbor node and thus reschedule its wake up time for the next cycle. In the case 2, the node might have failed. In this, there will be no sending of the hello packet to the node that is broadcasting the missing list header. If that particular node does not hear from the neighbor node for 2 consecutive cycles, it deletes its wake up schedule from the neighbor to save energy. Advantages of this protocol: the use of relative timestamps not only in the transmission of data but also in the establishment of communication and newcomers allows the nodes to operate in a synchronized environment where they can sleep and save energy the remainder of the time when they are not communicating. This protocol provides easy addition for the new nodes and also solves synchronization failures among nodes.